So let's begin our talk about polynomial functions. So in the very beginning of this chapter, we talked about degrees, leading coefficients, remember that? And I said, let's not worry too much about this because it's not really in context. We're going to come to it later. Well, today is later. All right? So let's look at this expression. This is a constant, right? It has no variables in it. To what degree is this expression? It's kind of ambiguous. 0. Because it has an x, it has a variable to the 0 power. Because anything to the 0 power is 1. So since it has a degree of 0, what is the leading coefficient of this expression? 9. Okay, let's continue, and it should make sense later on. This is a linear function, x minus 2. It's linear because it's to the degree of 1, and it has a leading coefficient of, leading meaning the first. Okay, let's do the next one, and then let's talk about leading coefficient. This one's a quadratic. Quadratic because it has a degree of 2. Quadratic functions look like what? Like a U, right? Quadratic function, like this. Okay, what is the leading coefficient of the quadratic function?
3.
You guys have that one. What do leading coefficients tell me? It doesn't tell me where I start. Okay, there's way too much talking going on over here. All right, so my question to you is, what is a leading coefficient? What does it tell us about a graph? What does that 3 tell me? The steepness. It tells me how steep it is. Right? If this was in this linear function, y equals mx plus b, that is my leading coefficient. It's the slope. Well, this is also the slope. This is also the slope. Right? Yes, sir. The degree is the greatest value of the exponent. For instance, Jesus, would you write this one like this? 4x plus 3x squared minus 5. Would you normally write it like that? No. Right? You would put that x squared in front because that is the greatest degree exponent. Correct? That degree right there, that x squared, tells me what that graph's going to look like. It's going to be a u. Right? The 3 in front of it tells me that it's going to be a skinny u. What else do we know about it? It goes up. Why? Because it's positive. What else do we know about it? It has a minimum of what? We don't really know yet. There's one more thing we can tell by just looking at it. The way? We already said positive. Not a perfect square. I heard it. The y-intercept is what? What is the y-intercept? -5. Okay, enough about that. All right, here's a cubic function. What's the degree of this polynomial function? 3. And what's the leading coefficient? 4. All right, so this one's always one of those things. Do you put it in there? Do you not put it in there? You're eventually going to have to understand what things like this mean. Is it necessary to do your homework tonight? No. but I've got to eventually get you used to seeing stuff like this. So what this says is, there is a number n, and that's the degree of my function. So the best way to explain this is that I always like to start at the right-hand side and kind of make sense of it. This statement right here is saying I have a to the 0, which would be my constant, right? The next term up would be a to the 1, x to the 1. Then the next term would be a squared, x squared. And the second term has a sub 2, x squared. What would be the next one? X cubed. And the next one? X to the 4th. The only thing that this little number down here is telling you is this one is the very first one. This is the second one. I know it says 1, but we start with 0, right? This is the starting point. Here's the next one. Here's the next one. Plus, dot, dot, dot. We don't know how many there are. But here's the greatest number one because we go in descending order. So this could be x to the 10th. And this says a to the n minus 1, x to the n minus 1. That means one less than that. What would that be? The 9th, then the 8th, and so on and so forth, 2, 1, 0. That's what this statement right here is telling you. Only we don't know. The reason we don't know is because it's a general rule. So they just put x to the n because it can go for any amount that n is positive. Right? Which takes us into our next section. All right, I will be able to evaluate polynomial functions and identify their general shapes. We're just talking general shapes today. All right, so let's come up with a general explanation of what a polynomial is. Super general.
Squared.
Okay. Squared. Has an exponent. Good. How about monomials have exponents, right? How about monomials added together? But within that definition, let's talk about what's a non-example. That's about the easiest way to come up with what a polynomial is. What isn't a polynomial? Remember we talked about this the first section of this chapter? What is not a polynomial? Somebody give me an example. A circle? That's a polygon. You guys are scaring me. Yes. No. Okay. Here's a polynomial. X squared plus x plus 2. What we just talked about, 9 could be a polynomial, right? Because it's got x to the 0. We also talked about polynomials have exponents that are either 1, sorry, that number is actually 1, or the exponents are, I should say, they're just integers. They're positive integers. Okay, so give me an example of something that would be negative. What? No. Yes, Mitchell. Perfect. How about x squared plus 1 over x? That is not a polynomial, right? Because that's got a negative exponent. How about one that actually has a negative exponent like this? There's another one. That's another non-example. X squared is a polynomial.
Yeah, but
This whole thing is not a polynomial. This whole thing is not a polynomial. There was one more example that we talked about. Yes. Something like this. Right? Because that's x to the 1/2. Is 1/2 an integer? No. There's 3 solid examples or non-examples of what isn't a polynomial. All right, that being said, pencils down. Let me get through these 3. State the degree and leading coefficient of each polynomial in one variable. I didn't think I needed a definition of what a polynomial is in one variable because this example will clear it up real quickly for you. This is a polynomial in one variable. This is a polynomial in 2 variables. What's the difference? This one has 2 variables. This one has 1 variable. We're looking for polynomials in 1 variable. So that being said, this is a polynomial in 1 variable. That's my first step. My second step is to state the degree. What's the degree of this polynomial? 4. And what is the leading coefficient? Good. Is this a polynomial in 1 variable? Not. A polynomial in 1 variable. All right, you guys, questions on these 2? Okay, you guys do these. Okay, so state the degree and leading coefficient of each polynomial in 1 variable. If it's not a polynomial in 1 variable, explain why. Is this a polynomial in 1 variable?
No, because the x.
Not a polynomial in 1 variable because it's not a polynomial. Right?
Yeah.
Right there. It's not a polynomial. What about this one? Yes, this is a polynomial. What's the degree of this polynomial? Excellent. 5 is the degree of this polynomial. That is the largest degree of this polynomial. What is the leading coefficient? -1. Because really, we should be switching these around, right? The negative x to the 5th should go first because it should be in descending order. Jacob? No, that's not right. Because x is not the slope. -1 is the slope. All right, any more questions? Good question, though, Jacob. Okay, pencils down. All right, so I'll be honest with you. When I was your age, these were my least favorite because I thought they were so abstract. I could never figure out what to substitute and what not to substitute. So I use analogies. So let's talk about this as functions. Functions are things where if you put in a formula, let's just talk about a machine. A machine functions, every machine has a function, correct? So if I were to talk about this, if this was a pizza machine, it would have this formula inside of it that produces pizzas, right? So I've got 2 different machines here. I've got a pizza machine, and how about a quarter machine? 2 different machines, 2 different functions. All right, let's talk about what we put into the function, because they can't work unless you put something into them, right? As simple as, I want 5 pizzas, right? You plug that in, you get a total, right? All right, so let's talk about what if I were to use the pizza machine. The first thing I want to do is I want to write out the formula for this pizza function. So this function is 2 times whatever we plug in for x cubed plus 6 times whatever we plug in for x minus 12. Well, what does this particular customer want to plug in for x? A cubed. Simple enough, right? So if we substitute in a cubed into this function, we will get 2a to the 9th plus 6a cubed minus 12. There's that one. Here's another one. This one is saying 5 times the quarter machine. With the quarter machine, if we put in 2a. So I have 5 times the quarter machine. What's the quarter machine formula? 5 times the quantity squared plus 4. What's my quantity? 2a. So if I substitute in that quantity, I get, I'm going to go nice and slow, 5. What is the quantity 2a squared? 4a squared plus 4. Now, keep going slow. 5 times, let's distribute. 5 of these 4a squareds is 20a squared plus 4. Now further distribute, and I get 100a squared plus 20. Everybody okay so far? I'm going to let you write all these down and give you an opportunity to in just 1 second. All right, let's look at the last one. This one's the most complicated one. This is saying I've got 3 pizza machines, right, that I'm going to substitute in a for a quantity, minus a quarter machine where I'm going to substitute in a plus 1. So let's not worry about what we're going to substitute in. Let's just talk about 3 pizza machines minus a quarter machine. So, 3 pizza machines. Well, what do the pizza machines look like? I believe they were 2x cubed. 2 times the quantity of x cubed plus 6 times the quantity minus 12. And take all that and subtract my quarter machine. Oops. We're actually going to put the quarter machine. What is the quarter machine? 5 times the quantity squared plus 4. All right, what did we want to substitute into our pizza machine? A. And what did we want to substitute into our quarter machine? A plus 1. Yep, whatever's in the parentheses you substitute in. So now I have 3 times 2a cubed plus 6a minus 12 minus 5 times, okay, let's highlight this guy. He's important. What is, that's not the color I wanted, what is a plus 1 squared? This is a very common misconception. Not a squared plus 2. A squared plus 2a plus 1. That's a perfect square trinomial. Because there's 2 of them. Very common misconception. So don't feel bad if you didn't catch it. That is saying a plus 1 times a plus 1. Okay? So if you can't do that in your head, you just need to come over here and just write yourself a little side note. Make sure that you get it right. Because if you get one thing wrong, the whole thing's wrong, right? Especially because you have to start at the beginning like that. So now I've got 5 times the quantity of a squared plus 2a plus 1 plus 4. Moving on, I can go ahead and distribute that now, right? So 3 2a cubes is 6a cubed plus 18a minus 36. I'm going to go ahead and just make sure that I go nice and slow on this. Minus this whole quantity here. I've got 5a squared, 10a's, a positive 5, and a positive 4. I'm going to combine these two to make 9. Is that okay? I think I'll do it on the next line. just to make sure we don't make any mistakes. Minus 5a squared, minus 10a. I'm just going to call it 9 now, okay? So this would be negative 9. All right, let's put it in descending order. What comes first? 6a cubed. What comes second? Negative 5a squared. What comes third? 8a, because 18a and negative 10a make 8a, minus 45, and that's our answer. Go ahead and copy these down. Okay, so I need you guys to try these two on your own. Okay, so back up here, what are we going to call this machine? A what? A bread machine? Let's make it start with an F. A freezy? Okay. How about French fries? A fry machine. Yeah, that's perfect. Okay. So I have a fry machine, right? And I'm going to stick in or substitute in b squared. So what is the function of my machine? 2 times the quantity squared plus 3 times the quantity minus 1. I'm going to substitute in b squared. Gives me 2b to the 4th plus 3b squared minus 1. All right, let's call this a Gatorade machine, right? But there's 2 different companies using this machine, right? Even if it's on different premises, it's still the same machine, right? So this first company says, I want 2 of them, 2 of the machines. Well, what are the machines? The machines function on a quantity squared minus 4. Another company wants 3 of the same type of machines that functions on a quantity squared minus 4. What does the first company input in? C plus 2. And what does the second company input in? 2c. This is the most complicated one. All right, so I've got 2 times the quantity. C plus 2 is a perfect square trinomial, which is c squared plus 4c plus 4 minus 4 plus 3 times the quantity. 2 c's 2 times is 4c squared minus 4. Everybody with me so far? Positive 4 and negative 4 make a 0 pair. That goes away. And I'm left with 2c squared plus 8c plus 12c squared minus 12. In descending order, what's my degree of my polynomial function? If the degree is 2, the leading coefficient is 14c squared plus 8c minus 12. Questions? Yes, Susan. This? This is x squared minus 4 and x squared minus 4. That's our function right there. Because it's saying the 2 of the functions where instead of x, we're going to plug in or substitute in c plus 2. And 3 of the functions where instead of x, we're going to substitute in 2c. See that? This says I've got a function of x. This is what it equals. This is my function. Then I say over here, well, what would my function be if I substituted in c plus 2 everywhere I saw an x? So everywhere I see an x, I substitute in c plus 2 right here. Just like, because it tells me I have, let's work, you have to work from the inside in. It's like saying g, the function of g when x is c plus 2. Do you see how that matches that? No? You're working from the inside out.
Hello.
Good. Melanie. Oh, there. Okay. We've got 7 minutes and I've got to cover this. Everybody pencils down. Let's pay attention. So like I said, this is in your book. Every single thing I'm going to write on this page you can copy down straight out of your book. I think what's most important is that I'm standing up here explaining it to you. All right, so the way I like to explain this is let's not talk about what we don't know. Let's talk about what we do know. So these two polynomial functions should look familiar to you, right? These are quadratic functions. What's the difference between them? One's positive, one's negative. Leading coefficient of this one is positive. Leading coefficient of this one is negative. Perfect. All right, let's talk about the degree. Now, this is a more generalization. We all know that the degree of this one is 2, correct? And the degree of this one is 3. I want to talk about what happens when the degree is even. So this one has an even degree. When you have an even degree, your end behavior is the same. For instance, see how as I'm going in this direction, kind of like shooting something off into the distance, right? Are you ever going to see it where it lands or where it goes? No, it just keeps going on and on and on and on, right? And then in this direction, it goes this way, on and on and on and on. So an even degree function, the end behavior is the same. Going this direction, going this direction. It's the same thing for this one. Even though it's going negative, aren't they both going in the same direction? The end behaviors are the same. Notice that an odd degree function, the end behaviors are opposite. One's going in this direction, one's going in that direction. Same thing with this one. This is an odd degree function. One's going in this direction, one's going in that direction. Let's talk about the leading coefficient on this one. The leading coefficient is positive, so it has the same beginning behavior as this quadratic does. See that? Only because it's got a cube right here, what happens when it comes down here, instead of going back up this way, is it falls down this way. And the end behavior ends up being down to the negative. So this leading coefficient is positive, but this leading coefficient over here is negative. It's like the negative side of the quadratic. So this leading coefficient is negative. Now let's talk about the end behavior. All right, so this is where it gets most complicated. I need everybody to shuffle into stop. Just pay attention. Okay, so what this is saying to us is my function, this is what happens to my function as x is in the positive direction. So if I were to put in any value of x in the positive direction infinitely in this direction, so positive infinitely, what would happen to my function? It would what? Increase or decrease? Increase, right? Infinitely. Do we know where it goes? Nope. Okay, so actually I'm going to change this out and put this on this side because that's on this side of the graph. Now let's talk about this side of the graph. Now what is x doing going in this direction? It's negative. So I would start with the x, because that's what you're putting in, right? The y, or the function of x, is as a result of what happens to x. So as we make x negative infinitely, what happens to my function? It becomes what? Positive. So as we go in the negative direction on x, my graph is going positive. Let's go back. Let's go over to the one we're familiar with and do this one. So which direction am I going in for this one?
Positive.
In the positive, right? So as I'm going positive infinitely on the x-axis, what's happening to my y-axis? It's going negative infinitely. And as I go in the negative direction on my x, what happens to my graph? It goes negative in the infinite direction. Starting to kind of get it?
Yeah.
All right, let's look at this one. See what it says. All right, let's talk about when x is going in the positive direction infinitely. What happens to y?
It goes in the positive.
It goes in the positive. And when I'm going in the negative direction on my x?
It goes in the negative
It
direction.
goes in the negative direction infinitely. And this one? As I'm going in the positive direction for x infinitely, it goes negative infinitely. And as I go negative, it goes positive. Good, you're almost through it. All right, what's my domain of this one? All real numbers. And my range is also all real, where my function, how did I write this one? Where my function is greater than or equal than my minimum. What about this one? My domain is all reals, and my range is also all reals, right? There's infinite number of y's in this direction and in this direction. What about this one? Domain is all reals, and my range is all real less than or equal than my maximum. Exactly. And this one?
All real and all real.
All real and all real. Now, hold on. You guys are getting restless, and the bell has not rung. All right. Let's look at this one. So, describe my end behavior.
Go to the fourth.
My end behavior are both going down, so is this an even function or an odd function? Oh, actually asked me to talk about my end behavior first. So, as my function of x, hold on one second, I got to show you at least one. My function of x is going what? Positive or negative? Going negative as x is going positive. And my function of x is also going negative as x goes negative. That's that part. Is this an odd or an even degree? Even, because they're going in the same direction. And state the number of zeros that this has. There's one, and there's one. That should be enough to get you through your homework. Have a great day, guys.